Hi, my name is Ricardo Medina, and this is the solution to the problem situation. To understand the problem situation, we have to understand what is a suspension system. So a suspension system basically is an automotive device that makes the car stable and cushions the car when you encounter irregularities on the road, like bumps or holes or things like that. And it does this basically by converting those irregularities into thermal energy. We can look at a suspension system uh, like like this: two masses. One mass is the 1/4 of the mass of the car. It's 1/4 because the whole car divides its mass into the four wheels. So we're only look at one wheel, and what it's 1/4 of the mass of the car. Then the unsprung mass, and these two are connected by a spring and a damper, and the unsprung mass is connected to the ground by a spring that represents a tire. Uh, and well, uh, we have the coordinates x, y, and u to represent the movement of each one of the masses and the ground. The movement on the ground would be an irregularity like a bump or a hole in the road. Then we can start doing our model of the state space model. First, we have to draw the free body diagrams of the components that move. So it's the two masses, and as you can see, there are two forces on M2 and three forces on M1, and there are the springs and the damper and the other spring. When we have this, we can start making our movement equations, which are these ones. These for M2 and these for M1. And with this, we can start doing our state space model by choosing the variables. So I choose these ones. And from them, we can start making our differential equations. Then we can put them into matrices. And here's our state space model. This state space model, we can input them in the simulation, which is this one. So here are matrices, here's the simulation, and we used as an input the road disturbance of a bump. And this is what basically comes out of it. So it's the movement of the two masses and the movement of the road, which basically is our u coordinate, our x coordinate, and our y coordinate. The road, you can see it's the red line that it's basically a bump. Then the yellow line is the unsprung mass, which closely resembles the movement of the road. So it doesn't differ as much as the blue line. And the blue line is the mass of the car, which oscillates higher and lower than the yellow line. And that's basically it for our simulation. And well, we have to understand that there's two types of suspension, active suspension. There's two types of suspension system: the active suspension system and the semi-active suspension system. What we just modeled was the active suspension system, and the difference between the semi-active and the active suspension system is basically that the the semi-active can change the damping coefficient uh, on the road and automatically via a mechatronic system. And why would we want to change the damping coefficient? Well, that's really easy because we'll use this for example. In a semi-active suspension system, the car would be driving here. Would be here, and then the sensors would react that there is a bump on the road, and it will send a signal to lower the damping coefficient to 0 so that the wheel can go up quickly. That's basically what the damper does. It's the stiffness of the suspension system. And if it's not stiff at all, then the unsprung mass will be easier to move and would move quicker. So in this situation, we want it to move quicker. And when it's already up, we want it to be a little more stiff so that the car doesn't oscillate as much. So we raise the damper coefficient. And then if the bump is over and it returns to the original level, then we want to lower the damping coefficient again so that so it's less stiff and it can move quicker downwards and the car doesn't take the heat. And that's basically it. Uh, to to model a semi-active suspension system, I think I would have to change the damper coefficient, which is the constant b, to a variable. Here's the constant b, and in our equations, here it is. It would be a variable other than a constant, and I would put it as an output, so that getting the data from the sensors, we can input them into our differential equations and our model, and then our model can tell us what to do in any situation, in any given situation, whether to raise it or lower it, and then that signal would go to the mechatronic system to raise or lower the damping coefficient. Nowadays, the damping coefficient, the semi-active suspension systems are very advanced because they can change and make adjustments up to 1,000 times per second, which is really quickly. And that's it for the problem situation. And as a conclusion, I can say that I did all the work because I didn't have a team. And the thing I'm most proud of is because I could make the state space model by myself, which at first seemed really daunting because there were a lot of things that I couldn't understand about the math. And yep, that's basically it. Thank you.